In this lecture, we're going to talk about Cepheid variables. These are stars that allow us to add
our next rung to the cosmic distance ladder. So what are they? So Cepheids are a class of stars that pulsate. They're yellow supergiants that are about 5 to 10 times the mass of the Sun and at about 6,000 degrees Kelvin. And what happens is their outer layers pulsate in and out, and their radius varies by about 15 to 25%. The reason for this is that there is an instability that develops in a certain part of the HR diagram that's caused by ionized helium in the atmosphere. What happens is the ionized helium in the atmosphere of stars actually scatters light very efficiently. It feels more radiation pressure, in other words. Light bounces off of it more. And that means that the radiation pressure in the atmosphere increases. And that causes the atmosphere to expand. Greater pressure means the outer layers of the star will expand a bit. As the atmosphere expands, it cools. And as it cools, helium will recapture its electrons and becomes neutral. But neutral helium doesn't scatter light very much, and so all that extra pressure is lost. The pressure decreases and the atmosphere contracts. That causes the temperature to increase, and that causes the helium to ionize again, and then the cycle starts over. So if we look at these stars and measure their apparent magnitude, we see a characteristic light curve that looks something like this, with a easily measurable period that is of order days. This is a schematic light curve of the original Cepheid variable, delta Cepheid. Here are some photographic plates showing a Cepheid variable go through its cycle. You can see it looks bright here on April 23rd, then dims down to its dimmest between May 9th, May 16th, and then back to its brightest by May 31st. So what's so useful about the region of the HR diagram where stars develop this instability is called, unsurprisingly, the instability strip. And it's in this region of the HR diagram, if a star passes through it as it's evolving along the subgiant branch, it will become a Cepheid variable. There are a couple of other class of variable stars which have similar instabilities, which I won't cover right now. So what's so useful about these stars? Well, the remarkable thing is that the mean luminosity of the star depends on the period of pulsation. What that means is if you plot the light curve about the mean versus the brightness of the star, the fainter the star, the shorter the period will be. The brighter the star, the longer the period will be. This was noticed first, and the exact relationship between luminosity and period of pulsation was discovered by Henrietta Leavitt in the early 1900s. And this is one of the most important discoveries in all of astronomy. The reason is that this gives us a way of measuring the distance to these Cepheid variables, and therefore the distance to any other things that are nearby. So for the nearby Cepheid variables, we already know the distance to the stars, and we already know what their luminosity is, what their absolute magnitude is. And so we can plot, for all the Cepheid variables we know, the period versus the luminosity, and they tend to fall on this nice tight correlation here. So imagine you don't know the luminosity of a star, but you notice that it is pulsating, and you measure the period of its pulsation. Well, that then means you can go to this graph, go to whatever the period is, say it's 30 days, read up from 30 days until you hit the curve, and that tells you that the luminosity is about 10,000 times the luminosity of the Sun. If you know the luminosity, you know its absolute magnitude. We see its apparent magnitude, and the difference between the two is the distance modulus from which you can extract the distance to the stars. So we can use this observed relationship to measure the distances to stars that we don't already know the distance to, so long as we can observe their period of pulsation. Now, up until this point, all our methods of measuring distances to stars work only within our own galaxy, but we can see variable stars and we can measure their period to much, much greater distances. In fact, we can measure them out to about 40 million parsecs, which easily takes in our local group of galaxies and goes some way beyond. So why was Henrietta Leavitt's discovery so important? Well, it was that discovery that allowed us to actually discover the existence of other galaxies. Up until this point, all the stars that we saw, we thought were within one massive collection of stars, a single galaxy. But it was the discovery of Cepheid variables that allowed us to measure the distance to stars in certain nebulae, like the Andromeda nebulae, and figure out actually they were much, much further away than any other stars we knew, and that these nebulae were actually other galaxies, other enormous collections of stars. So our knowledge about galaxies comes from our ability to measure distances using Cepheid variables. That is our next rung on the cosmic distance ladder.